The human body, its form and shape is dependent on collagen, an essential protein found abundantly in all mammalian connective tissues such as skin, cartilage, muscle, bone, tendon, teeth and eye. Collagen is vital for the structural integrity of the body. Any imperfections or instability in its structure causes diseases such as hypermobility syndrome, osteogenesis imperfecta, and Ehlers-Danlos syndrome. 50 years ago, we did not know what caused these conditions. This understanding became possible only after the structure of collagen was decoded. It was in a small and relatively unknown laboratory in Chennai that a young physicist of C.V. Raman's heritage, barely 32 years old, unraveled the basic structure of the protein, a problem that was eluding the greatest structural biologists of the time. The discovery was to put India on the world map of modern structural biology. The young researcher was G.N. Ramachandran, or GNR as he was affectionately called, one of the greatest scientists that India has produced. When Ramachandran entered the field in 1952, those were momentous times for molecular biology. A year before, Linus Pauling had discovered the alpha helix, one of the basic structures of all proteins. The double helix of DNA, which carries the genetic code and forms the basis of all life, was discovered by James Watson and Francis Crick in 1953. But the structure of the most important protein, collagen, which accounts for 1/3 of all proteins in the body, was not known. It had engaged many top researchers in Britain and the US, Pauling and Crick among them, but the problem had proved to be complex. It was in this charged atmosphere that GNR, unknown in the field and working practically alone but armed with extraordinary intellect and intuition, had begun his experiments to determine the structure of collagen. The only way the structure of biomolecules could be studied in those days was through X-ray crystallography. GNR, having worked in C.V. Raman's lab in Bangalore and later with Lawrence Bragg's group in the Cavendish Laboratory in Cambridge, was already an expert in the field. When the Vice-Chancellor of Madras University invited him to head the new Department of Physics, he readily agreed and decided that X-ray diffraction and X-ray crystallography would be the focus of research in his laboratory.
The appointment in Madras was rather unique for anybody in India at that time. Namely, that the department had reasonable amount of space and no previous equipment was there and no previous heritage was there, so that I could develop it just as I liked.
Raman was not able to appreciate the tremendous new opening of structural biology. And GNR had recognized the importance by going to Cambridge and interacting directly with the people working on those areas. But then he had made up his mind to do that type of problem in physics in Madras. Those are all very crucial decisions.
But GNR did not know where to begin. A chance visit by J.D. Bernal, the famous British crystallographer and chemist, to Madras in 1952 proved to be the turning point in GNR's career. In a casual conversation, Bernal suggested that though many structures for collagen had been proposed, none of them was satisfactory, and the problem still was very much an open one. GNR and his associate Gopinath Kartha had to set up the experiment right from scratch, generate the data and interpret them.
The most remarkable thing about G.N. Ramachandran is with just one X-ray machine in this otherwise primitive country to have done something so fundamental. You see, that is the peak of his work.
Even the source material wasn't readily available. GNR first tried shark fin ray collagen, but the diffraction image was poor. He then approached Dr. Nayudamma, director of the neighboring Central Leather Research Institute, to give him a good fiber of collagen. To GNR's surprise, Nayudamma obtained a big tube full of kangaroo tail tendon from Australia, from which fibers were extracted at CLRI. Like Raman, his guru and mentor, he demonstrated that first-rate science can be done even with limited resources if you have the right ideas. Proteins are essentially long polymers of different types of amino acids called polypeptides. Collagen is an insoluble fibrous protein which, unlike globular proteins, makes the X-ray diffraction patterns difficult to interpret because of their diffuse nature. It was also tough to model its structure as even its sequence was not known. GNR's insight and intuitive genius enabled him to overcome these problems. In a remarkably short period of 2 years, GNR and Kartha published the first path-breaking result in Nature magazine on August 7, 1954. Though it was a prototype of the collagen structure, it introduced the fundamentally new concept of the triple helix. In a subsequent paper, which also appeared in Nature in September 1955, GNR proposed the coiled coil form of the triple helix, the collagen structure as we know today. The collagen triple helix has 3 intertwined minor helical polypeptide chains forming a closely packed right-handed major helix around a common axis.
It's amazing how Professor Ramachandran, with an extremely limited data that you get out of the fiber diffraction pattern, could arrive at the structure of collagen. The model building was a major tool those days. He devised these planar units of the peptide, and several of these can be joined together. This has several degrees of freedom, and Professor Ramachandran worked out the optimum structure for each of these chains and then placed 3 chains such that they have a 3-fold symmetry. And he also organized each of these chains staggered by about 3 angstroms, so that the glycine comes exactly at the center.
At that time, all he knew was 1/3 of collagen was glycine. He made the extra step that every third is glycine, and that fitted his triple helical structure. Ramachandran thought deeply geometric. His mind worked that way, and there was an intricate way for him algebra and geometry connected. And he was fascinated with his coil-to-coil structures.
GNR himself says he got the idea of the coiled coil structure from astronomy. Just as the moon's rotation and its revolution around the Earth are so coordinated that the moon always presents only one face towards the Earth, GNR conceived that the pitches of the 3 helices and that of the main helix are so coordinated that the glycine residue always faces the center of the helix. The physicist in him provided that leap of imagination. Acknowledging this, Pauling had remarked, in 1955, Professor Ramachandran and his co-worker Gopinath Kartha described the striking triple helical structure of collagen that is now being accepted as generally correct. Although I may have some feeling of regret that Professor Corey and I did not succeed, I may point out that the problem was a very difficult one and that Professor Ramachandran and his co-workers deserve great credit for their successful attack on it.
In the context of double helix, where Chargaff already provided A plus G is equal to T plus C, Wilkins' laboratory got the diffraction pattern, Watson-Crick's problem was much simpler. This tremendous splendid isolation in Madras allowed him to think original with such limited resource, which is definitely far more commanding than the environment in which Watson-Crick discovered double helix.
After the alpha helix and the double helix, the deciphering of the triple helix was a landmark in structural biology, leading to many subsequent discoveries of triple helical structures. The work immediately brought him shoulder to shoulder with the giants of structural biology and the new department at Madras University into international reckoning.
I never studied mathematics beyond high school and intermediate level. Luckily, my father, Sri G.R. Narayanaya, was a professor of mathematics, and even before I joined the physics course, I had learned from him all the mathematics that was needed.
This would later play a crucial role in the manner in which he approached problems in his research. In 1939, he joined the famous St. Joseph's College in Trichy. After completing his graduation with honours degree in physics, Ramachandran joined the Electrical Engineering Department at the Indian Institute of Science for his postgraduate degree. Soon he came to be greatly influenced by C.V. Raman, who was heading the physics department. This resulted in GNR switching from electrical engineering to physics.
Somehow I could not take the non-rigorous nature of the teaching. Therefore, I met Professor Raman with great courage and requested him to kindly take me in his group. In my career, I have found that it was Raman's influence that has shaped it.
Despite his groundbreaking work, recognition did not come easily to GNR. In fact, his achievements courted controversy instead. In a classic battle between East and the West, Francis Crick, riding on the double helix fame along with Alex Rich, began to pick holes in GNR's triple helix structure, actually calling it wrong. Crick and Rich contended that the two hydrogen bonds between the polypeptide chains per helical turn in the GNR-Kartha structure was not possible because of short contacts between some atoms. Instead, the two put forward a structure with a single hydrogen bond, claiming it to be the correct one. However, while their public rejection of GNR's work in nature was sharp, Rich and Crick privately in a letter gave him credit for his discovery, saying, "We feel that your type of structure is in the right lines and the collagen problem has changed completely as a result of your work." It is, however, curious that while Nature took more than 4 months to publish Ramachandran and Kartha's work, papers on the collagen structure by two British research groups, one of which was the Rich-Crick paper, were published within a month of their submission. The other was a paper from the King's College Group in London. Interestingly, while one of the referees of the GNR-Kartha paper was Crick himself, the other group had got to know of the paper through Bernal, to whom GNR had sent his manuscript. Indeed, in a letter that Kartha wrote to Ramachandran from Cambridge in December 1955, he says, "The general idea seems to be that the publication of our paper was purposely delayed by months for them to work up our idea after seeing our manuscript."
It seems that big names of the game of the science those days were disappointed that how come a scientist from an unknown laboratory from a country of ex-colony of British could come out and solve a structure at which the British scientists have been so long attempting and unable to solve it.
I think the collagen structure was an absolute landmark in its time. It is also essentially correct as he proposed it in 1954. The Crick-Rich controversy of 1955 was, I suspect, a case of trying to nitpick at deficiencies in the Ramachandran-Kartha structure. There was nothing wrong with the triple helix. There were a few details which might have been in doubt. But in the years that have followed, I think even those details have turned out to be essentially correct.
If you take the DNA structure, today's DNA structure is not the same as Watson-Crick proposed. In that context, can we say Watson-Crick is wrong?
Though GNR took the criticism to heart, he responded to it in a manner that is typical of brilliant minds. In 1963, he, along with his students V. Shashishekaran and C. Ramakrishnan, set out to establish general criteria to determine whether particular protein conformations were acceptable or not. This resulted in what is today called the Ramachandran phi-psi plot, or simply Ramachandran diagram. A protein molecule can be characterized by two rotation angles, phi and psi, that specify the relative orientations between any two planar peptide units in the long chain. GNR's group asked the question whether all values of phi and psi result in acceptable and meaningful protein structures.
If I want to talk of protein, I must take a very basic thing. If I know how to add one-digit numbers and carry over, I can add even 10-digit numbers. Like that, a small part of the protein has to be picked up, which can be examined. First idea, namely that the protein can now be examined in terms of peptides. Number two, the distances can be calculated. Number three, a criteria can be applied.
The Ramachandran diagram provides a simple two-dimensional graphic representation of all possible protein structures in terms of the rotation angles. The analysis was simple and elegant, but because of its apparent simplicity, the power of the technique was not fully realized immediately.
Everybody thought this is only a theoretical work, it will lie there like this. But when the first structure of myoglobin was solved and it was plotted on the map, the points just fell into the map.
But as more and more biomolecular structures are being determined, the plot serves as a confirmatory tool to determine whether a proposed structure is acceptable or not.
And that is what the Ramachandran map is now used with the globular protein structures, whereas it was original thing was to use it with a fibrous protein, which are number is less.
40 years after it was formulated, the Ramachandran map still remains a fundamental tool for protein confirmation.
I use his work on the Ramachandran map almost every day in my own research, and many refinements have been attempted, but they're all icing on the cake.
Another aspect of the collagen structure that engaged GNR right into the 70s was the stability of the collagen structure and the role of water and the hydroxylation of the amino acid proline in promoting the stability. Defending the basic two-hydrogen bond structure of the triple helix, GNR and R. Chandrasekharan suggested in 1968 that while one hydrogen bond was direct, the other could be mediated through water.
To my own surprise, and I think to Professor Ramachandran's surprise also, what we found was the water molecule which they had put between the two chains as forming a hydrogen bond could also be linked to the hydroxyl group of hydroxyproline. It kind of provided a very nice and neat explanation for how the hydroxyproline could help in stabilizing the collagen structure. And in addition, in fact, if we have this hydroxyl group also has another hydrogen attached to it, which can then form hydrogen bonds with another triple helix, a neighboring triple helix. So it not only forms an intra-triple helix stability, but also the whole collagen fiber, which as you know consists of multiple molecules, it actually gives that additional stability also.
That's Ramachandran. He would continue pushing, try to refine, and so on. That is the way he worked.
In 1970, the atmosphere in the university changed drastically. The Vice-Chancellor, Sir Mudaliar, retired, and with him the patronage GNR's department enjoyed also ended. GNR found it difficult to adjust to the administrative regime under the new Vice-Chancellor. This forced GNR to leave Madras. He spent a year in Chicago and then moved back to Indian Institute of Science, Bangalore, to create the new molecular biophysics unit there.
Only Ramachandran could have put together a group like this in MBU. And also his choice in retrospect was very interesting. All the computational people he brought from Madras, his own colleagues. In Madras, the experimental work was primarily confined to X-rays. Much of it was theoretical work. Whereas Bangalore, Institute of Science being what it is, with such a lot of experimental work going around, he could build in Bangalore a very composite group. And in fact, the strength of MBU, the way he visualized it, the way he built it, was extraordinarily interdisciplinary. Eventually, Ramachandran, the way he envisaged it, is to bring to bear on a central issue all possible techniques. He bequeathed these two major schools, the Madras group and the Bangalore group.
But GNR was a man in a hurry who was thinking far ahead and was aware of rapid developments elsewhere.
He set up a tone for research that was very urgent. The pace with which things at that time were being done in India is not the pace in which he was thinking. He was, in my opinion, completely out of step.
If Professor Ramachandran were there now, probably he would have been more successful than what he was, say, 30 years ago. He did try to form groups with people in biology division, people in chemistry, as well as people in physics. But I think not many people were forthcoming to see this. And I would say that many of his frustration resulted out of this.
While the structure of biomolecules formed the mainstay of GNR's research, his primary interest in X-ray diffraction and crystallography, which was Raman's legacy, continued to engage him, and this resulted in several highly original contributions. In 1971, with A. Lakshminarayanan, he published a seminal paper giving the theory of reconstruction of three-dimensional images from a series of two-dimensional projections, which has applications in computer-assisted tomography. Ironically, people who discovered the technique later got the Nobel Prize in 1979. After a year's sabbatical in the US in 1977, GNR moved away from mainstream biology research. He got interested in logic and philosophy and mathematical biology.
When he left, MBU was more or less like what you call Hamlet without the Prince of Denmark. We all, at some point of time, we felt orphaned.
GNR may not have received the recognition that he truly deserved, but there is no denying that his work was Nobel class, as a letter from K.H. Gustafsson, the famous Swedish chemist, testifies.
I recall Professor Nadama coming into the class one day and reading a letter from Professor Gustafsson, who was a very noted protein chemist himself of those particular time. The letter read sum and substance, as Professor Ramachandran was a noble material, and his lecture on collagen was truly inspiring and outstanding, and he really hoped that Professor Ramachandran will be given the Nobel lecture very soon.
I've always held the view that GNR deserved a Nobel Prize. His work on polypeptide stereochemistry is an absolute cornerstone for the field. The unfortunate thing is, I think GNR was ahead of his time. So his work is much better recognized, more widely used today than it was in the 1970s when he was still an active and visible scientist.
Nobody would have complained if GNR got a Nobel Prize, and many people are sorry that he didn't get one. So as I said again, when Hartmut Mitchell said, what you call, many Nobel laureates have been forgotten, but GNR is still remembered. So in the long run, I don't know how important it is.
Though late in coming, he was elected Fellow of the Royal Society of London in 1977, and in 1999 he received the prestigious Ewald's Prize of the International Union of Crystallography for his outstanding contributions to X-ray crystallography.
But one thing I must say, in 1959, when he had already finished this collagen work, I thought the work of that quality and caliber must get recognition internationally in some way. And if not internationally, at least nationally. See, nationally, nobody did anything special for him for having made such a major discovery. Well, something like Royal Society should have elected him as Fellow of the Royal Society in 59, not in 77 or whatever. I don't think we ever honored him properly in this country. I don't think he ever got a proper title in India, Padma Awards or whatever. I feel very sad.
Though GNR is remembered for his science, he was a man of many parts. He enjoyed music, wrote poetry and played cricket, facets only those close to him knew about.
He took the entire family and drove single-handedly the car all over South India, went to Jog Falls, etc., etc.
But what sets him apart as a human being was a sensitive nurturing of people. Whether it was an assistant or women researchers, who he initiated and encouraged to enter his world of science.
என்னை வந்து ஒரு ட்ரைனிங்காக கொடுத்தார். லேத்தில், அப்புறம் ஃபோட்டோகிராஃபர், ட்ராயிங் போடுறது, அதெல்லாம் எனக்கு சொல்லி கொடுத்தாரு. அதுக்கப்புறமா எக்ஸ்ரே லேபில் கூட்டின்னு வந்து எப்படி கேமரா செட் பண்ணோம், எப்படி அலைன்மெண்ட் பண்ணோம், அந்த மாதிரிலாம் சொல்லி கொடுத்தாரு.
For him, merit was the only criterion. I don't think that the idea of gender ever crossed his mind, that somebody should be not allowed to do research because they were girls. So to that extent, I think he was ahead of his time. He tried to even appoint some women professors in Madras University, which is supposed to be one of the traditionally conservative university.
But his exhaustive life work was suddenly interrupted by illness. He was forced to retire from active research and spend the rest of his life in relative isolation, supported by his wife Rajalakshmi till her death. GNR left the scene of active research in structural biology more than a quarter century ago. Yet his outstanding contributions continue to impact the field, which is advancing rapidly in terms of techniques and concepts.
Nobody realized 40 years back that today's rationalized drug discovery, where the protein crystal structure, inhibitor docking, are all based on the fundamental principles of Ramachandran.
The technology of crystallography, the methodology of crystallography, that again GNR's contributions have been very enormous. Something called anomalous dispersion, use of anomalous dispersion, very vibrant now. And Fourier transformation. Fourier transformation means not only the techniques he proposed, the way GNRs approached the subject illuminated the whole area. Collagen now is a very active field. Collagen has suddenly bloomed. So whenever you think about collagen, again you go back to GNR.
GNR passed away on 7th of April 2001, but his brilliance remains undiminished and his legacy lives on.
He was a scientist who was breathing science, eating science, and living in science.
In fundamental science, GNR's work stands is probably the most outstanding.
Here was a man who had achieved an enormous amount working in India.
We won't even call him Ramachandran, we call him professor. There is only one professor in the world for us.
The time to rejoice that a man like him existed amongst us.
He was pure Agni. His passion was science.